Welcome back to the classroom. My name is Mr. Wong. Today we're going to be covering Module 8, Implying Chemical Ideas. We're going to be investigating Inquiry Question 2, Analysis of Organic Substances, with a focus on the infrared spectroscopy and also the technique that we use in that to analyze simple organic compounds. Now your textbook references are this. And we're going to be looking at the function of infrared spectrometry, how do we use it, how does it function, and also the types of spectras that we form. How can we interpret the spectras in order to understand the molecules that we are trying to observe? So just a quick recap on what we talked about from the previous lesson. Is what is an electromagnetic wave? Remember, electromagnetic waves are obviously a wave that responds from oscillating magnetic and electric fields acting perpendicular to each other. The infrared spectra, or the infrared waves, they are just behind, or they're just, in terms of frequency, they're just behind visible light. In terms of wavelengths, they're slightly longer. And there is a whole range of infrared spectra as well. Now, using in this range, we can use to identify different types of functional groups and different types of bonds that are being formed in the molecule. So with infrared spectra, you can see that's the equivalent wavelength of it, and we're using it to look at the interaction that this radiation has with the bond, to look at the type of molecule that is present. Now, just to give you quick pointers up, the infrared spectra actually uses infrared radiation that will eventually collide with the molecule. That radiation is absorbed by the molecule and it's projected as the energy of vibration for these particles or of these bonds. Now, specifically speaking, not all wavelengths are absorbed. There is a specific value that of this infrared spectra that will be absorbed to the specific bond. So each bond will have its own specific range in the infrared spectra that it will absorb to cause these kind of vibrations. Okay, so that's our investigation for today. You can see this is an infrared spectrograph, and this is the setup for the infrared spectra. Okay, so infrared spectra is a very important technique that we use to help us identify the type of bonds that are being formed. So is it single, double, triple? And it can also signal the type of functional groups that are present or not present in that particular compound. The wavelength is relatively long in comparison to what we talked about with light waves, so it's on the longer side. Whatever you sense in terms of heat, anything that makes you warm, that radiation that you feel is actually infrared. So you can almost say it's like the radiation of heat in a way. It's relatively cheap and it's a pretty easy technique to use. So let's have a look. Firstly, let's get a bit of background on how infrared spectrometry works. It's based on the ability of particles to vibrate or different bonds to vibrate. Now, when I say vibrate, it implies that it's stretching, rocking, wagging, twisting, scissoring. So these are all the different types of vibrations that can occur in a bond. And what we do know is in all molecules, at any temperature above absolute zero. Now, if you recall, absolute zero is a theoretical number that we believe there is absolutely zero, or the temperature is zero. So absolute temperature, or absolute zero, I'll say that again, is where we assume there's no vibration of compounds, of bonds. So anything above absolute zero, we will see some type of vibration here. These vibrations are caused by the absorption of infrared radiation. Okay, and they all have a specific frequency of when they vibrate. So, as in what interval of time does it take for them to go backwards and forwards when they're stretching or when they're rocking. So there's a specific interval there, and that will dictate the type of wavelength that will be used to calculate this particular stretch. Okay, so molecules will absorb infrared energy. In a way, it's self-explanatory. Radiation is energy at a frequency corresponding to the frequency of the bond's natural vibration. So it detects the variation absorption within a sample, and that measurement we use is called the wave number. Now the wave number is the inverse of a wavelength. The inverse of a wavelength, if you think about it, is just frequency, or not frequency, but the wave number is a measurement of the frequency of a vibration of a bond in the molecule. The absorption of the energy results in an increase in the amplitude of the vibration, also called resonance. Now, in physics, just to explain what resonance means, we know that each bond will have a natural period or time period where it stretches backwards and forwards or vibrates. If we can supply it with energy to allow it to vibrate at that same frequency, so when you have a natural vibration and the energy driving that vibration are equal to each other, you get resonance, which is the two of the same frequencies adding on to each other, causing an increase in the overall amplitude or vibration. So we're causing this vibration to get larger in a way. Okay, so you can see once the bond has absorbed that infrared energy, we cause it to vibrate at a longer stretch. Okay, if you actually have a look, these are a little graph to show you what we talk about in terms of absorbing energy. To give you a bit of an idea, obviously this isn't the infrared spectra of the different types of greenhouse gases, but it does show you a type of functional groups that will absorb infrared radiation. Now we know that with global warming, the greenhouse effect, the way that the greenhouse effect works occurs when the sunlight comes in, strikes the earth as UV light, the earth will try and then absorb that energy and release infrared radiation. Now, if we have greenhouse gases, the greenhouse gases will absorb a specific range of that infrared. So it absorbs that infrared and it will project it back onto Earth. So that's how the greenhouse effect works. If you actually have a look at the different types of bonds that we have here, you can see the carbon-oxygen double bond. So that's the type of bond that you would see for CO2. You have the oxygen-hydrogen bond, which is prevalent for water. You can also see that there are multiple absorptions of the same bond type. The reason being is because of the different types of vibrations that you see. So you can see here the reason why greenhouse gases are so crucial in our understanding is because of its ability to absorb infrared radiation. Okay, so how does infrared spectrometry work? It essentially works by having these molecules absorb infrared radiation, causing the vibration of the molecule to undergo some kind of asymmetric stretch. Okay, and this causes an uneven distribution of charge. So if I have carbon dioxide, which just by looking at this, it's symmetrical, right? So both sides are, equal distance apart. When it absorbs this infrared radiation, when it vibrates, the carbon dioxide, one side of the oxygen could be a bit closer, one side of it could be further stretched out, and that could cause a distribution, an opposite distribution of charge. So, the further away it might be partially positive, the one that's closer together might be more partially negative. And so we get this temporary dipole moment. And it's this temporary dipole moment that enables the absorption of infrared radiation. So this could be the reason why a lot of symmetrical looking molecules might still end up absorbing infrared radiation, because the way they vibrate can still make them become a temporary dipole. And the infrared spectrometry will use the molecule's ability to absorb the specific range of infrared radiation to observe the specific types of bonds that's inside. So that could be the vibration, the number of bonds between molecules, or it could be the functional group that's involved. You can see here with ethanol the different corresponding lines that we see. So we have the carbon-hydrogen bond being related to this particular spectra here, this oxygen-hydrogen bond here, the hydroxyl group, that corresponds with this spectra here, and then we have the carbon-oxygen bond, which corresponds with this functional component here. Alright, so there's a lot of different types of bonds that we will be able to observe in the infrared spectra. So the first thing we need to look at is what affects these vibrations, and what can that tell us in terms of the absorption patterns in the infrared spectra. So let's have a look at the different factors that affect vibration. So the first one is vibration type. Generally speaking, it's easier to bend than stretch. So bending vibrations are of lower energy than stretching for the same type of bond. If we have a look here with the stretching vibrates a lot faster. So what that essentially means, there's more energy, it vibrates a lot faster, it has a higher wave number stretching than in comparison to bending, which has a lower energy, so there's a slower oscillation. The next one we have is the type of bonds. So single bonds have lower energy, they're weaker. Triple bonds, so greater amount of bonds, is stronger, has higher energy. You can see here. That corresponds also with the wave number here. So a carbon-nitrogen single bond is around this range here, while a carbon-nitrogen triple bond is around this range here. So it has more energy, it will oscillate a lot, needs a lot more energy to oscillate. The next one we have is the strength of the bond. So again, like we said, strength of the bonds will relate to the number of bonds between each element. So we have the carbon triple bond to the carbon single bond. You can see the bond energy is progressively going higher with the additional bond. That also corresponds with the greater amount of energy required to cause it to oscillate. We have another one, which is the type of mass. So the mass of the atom to the bond is also going to affect how fast it's going to oscillate. So the heavier the atoms vibrate, will tend to vibrate at a lower energy, so they vibrate a lot slower than it is for the faster vibrations of the small atoms. So carbon, chlor, and chlorine will absorb a wavelength of that, or wave number of that particular range, whereas carbon, bromine will absorb infrared radiation of that particular range there. Okay, So it means that energy needs to be absorbed for this to vibrate. This one will vibrate a lot faster. Okay, and so there's that particular range there. So we see with the carbon hydrogen one, it will absorb a wave number at a much higher range than it will for the carbon and bromine absorption there. Simply speaking, the higher the absorption number, the quicker the oscillation. The lower the absorption number, the lower the oscillation of the bond. Okay, the next bit we're going to talk about is obviously the technique of infrared absorption. Now there's two particular components you need to take into account. One is called absorption, one is called transmittance. To put it simply, transmittance is how much light is going through the sample. So if we assume that we have 100% light traveling from the emitter of the infrared to our detector, that's what we're trying to measure here. How much light do we get going through? The absorbance is a technique we use to calculate the amount of infrared that is absorbed by the sample itself. Okay, so I'll repeat that again. If we're using a control sample in comparison, our transmittance measures the amount of light that passes through the sample. Our absorbance measures the amount of light that was absorbed by the sample cells. So our sample cells are these examples here. How much light do they absorb in that component? And when we go through this, we actually use a reference cell. So we have the sample and we have a reference. Now this is obviously just the control group that we use. The reason we have that is to sort of get a sample size of what the base value we have within the system. So if we already detect some background infrared radiation, we can subtract that from the calculations measurements of our sample. The way infrared infrared spectrometry works is it will split a light into two components. So source of radiation, it will split into two. The infrared radiation will go through the sample and your reference. That is cemented together and they are then recombined at the detector, which we then record. By using that, we can work out the wavelength most appropriate to analyze this particular sample, and we can also detect if there's any discounts in the final results that we need to take into account based on the background radiation. Okay, the next bit we have is interpreting infrared spectra. So you can see this is the actual component of it. Just to get a gauge of what it is, on the y-axis we are measuring the percentage of transmittance. So how much of the light is going through from the emitter to the detector. You can see obviously if there is a functional group present or bond present, we are absorbing most of that light coming through. And then we also measure it via the wave number. So in terms of how fast that particular bond is vibrating through. You can see different types of bonds here and relate it back to what we talked about in terms of the factors. So we have the carbon-hydrogen stretch and bend. We did say that the stretching occurs a lot faster. So you can see it's at a much higher wave number than it is to bend. We can also look at it based on the functional groups. So this one here, oxygen and hydrogen is a smaller atom combination than carbon and oxygen. So you sort of see that one there. And then obviously we can also differentiate in terms of double bonds as well. So there's that. Alright, generally speaking, there are two regions of a infrared spectra. One is called the functional group region, the other one is called the fingerprint region. Now, what tends to happen is we look at the peaks within the functional group region. The reason being is the fingerprint region from 1500 to 500 contains a large mixture of different peaks, and so it can be quite difficult to interpret. So we generally go with the left hand side first to work out the main functional components, and then we will use the finger region to confirm the identity of our compound. So as you can see, this is great in finding our functional group. You will need to use other techniques such as mass spectroscopy, HMRI spectroscopy as well, including with infrared spectra. If we have a look at the peaks here, do remember though, the infrared absorption data is all given in your NESA datasheet, so you can see each stretch that you see here is directly related to a different component of bonds. Okay, so this is what we have here. If we actually have a look, there are two references of the hydroxyl groups. One will represent the alcohol. We tend to sort of want to say the smooth tongue on the infrared spectra represents the alcohol. The sort of hairy beard represents our carboxylic acid. Obviously, if you want to work out if it's carboxylic acid, you'll also need to work out if there is the other functional group, the other carbon-oxygen group there as well. So that's where you can sort of see the OH bond, but it can imply two different types of functional groups. If we have a look, that is an example of the alcohol group there. That's another example, that's another example, that's another example there. That is also, with the exception of the last example, which is this one here, you see there's not much of an absorption there. Not much of a smooth tongue either. So each of these bulbs represents the hydroxyl group of alcohol right there. That wouldn't count because, as you can see, that's not the shape we're looking for. The other one here, this is not a nice example to show the carboxylic acid. We call it the beard version. So it's, you can see sort of like a poorly cut out beard shape. It's a very broad spectra, so that sort of shows you it does absorb a large range of infrared radiation. The typical peaks of the carbon double bond oxygen group is what we call the sword-like structure, so a collection of swords that shows you the carbon oxygen double bond, and you can see it's in a lot of different types of functional groups. So you have the aldehydes, the ketones, the esters, the carboxylic acids. So what you would need to do if you saw the bearded version of the OH group, then you also need to work out if you see the carbon double bond to oxygen sword-like structure there. It's also the strongest peak on the spectra, so you can see it basically absorbs the most amount of infrared radiation, which is kind of why they sort of say carbon dioxide is quite an issue when it comes to the greenhouse effect. You can see if we break it up, we can find the different functional groups. So using ethanol as the example, we can find the alkyl group here. We can find the carbon-hydrogen bond here, a really sharp sort of drop here. We can find the carbon-oxygen bond, so that's that bit there. And then we can also find the carbon-carbon double bond. You can see these ones more so tell you about the general structure. These ones here tell you more about the functional group that's inside the actual compound. Alright, so just a couple of takeaway points for you when it comes to interpreting infrared spectra. Stay on the functional region of the graph first. Look for obvious peaks, so the any smooth tongues or beards. That gives you a broad peaks of the OH bond. Any sharp sword-like sort of spectra points, strong sharp peaks, that represents the carbon double bond with oxygen. If you have these following combinations, you'll have these following functional groups. So keep that in mind. You should also probably maybe copy this down, so that's a point that you can look into. So I'll just write the copy sign here, just in case. So keep that in mind. You can go through a couple of question points as well. So go to this question, have a look and analyze the structure of the bond or of the actual molecule. So the molecular formula is C3H6O. I'll go to the answers. So that, what we believe that structure to be is ethanoic acid. So have a look at what you can see. Alright, some other questions for you to consider. And that basically concludes our lesson for today. So we went through infrared spectra, we worked out how it works, what's the science behind it. We looked at the factors that affect the different type of spectral lines that we see. We worked out that it helps us find the functional groups and the type of bonds of that. Anyhow, do remember infrared radiation is just one way of looking at the bonds and the structure of the atom or of the molecule. You do need other techniques to help you round off a better picture of everything as well. Anyhow, thank you for joining me today. You're always more than welcome back into the classroom. And if there's anything you didn't quite get, please rewatch the video. Until next time, take care and goodbye.